So this is 4.1 part 2, which deals with what's called arc length. Once again, even though you have not been assigned a textbook, you have access to the textbook in Google Drive. I've shared it with you. The 4.1 is talking about the textbook section. If you need additional practice, you have that textbook as a resource. So if you feel that after writing exams you weren't fully prepared as you wanted to be, in addition to all the review materials I give you, you can certainly pull up the textbook next time and use stuff from there. Including, but not limited to, the chapter reviews and going through their examples. There's all kinds of stuff in there. The textbook isn't bad. It's not a bad textbook. It's a good textbook. I just prefer my own sets of problems for practice. We're going to be solving problems today using the relationship between arc length, radius, and rotation angle. So when we take a look at this diagram on the right, when we have a particular circle, any circle you want, with a certain radius, if we rotate that radius, we can think of it as an arm, but if we rotate that radius through an angle theta, we trace out what is called an arc length. And I hope that it's obvious that these things are interconnected somehow. I mean, I'm giving you the formula, but wouldn't you agree that if the radius of the circle were larger, the arc length would be larger? And if the angle were smaller, the arc length would be smaller. These things are all related. And the reason this formula works, I'm going to just explain it briefly, is based on the definition of a radian. A radian for a rotation angle is what you get when you trace out one radius. So if I were to trace out 2 radii along the edge of a circle, that angle would be 2 radians. So if you take, everybody, the number of radii that the arc length is and divide by the radius, you'll get how many radians there are. If you're interested in where that comes from. Now later on when you try to rethink that, it may not make sense to you. But I just wanted to give it to you briefly. The only way this is going to work though, the only way if you divide the number of radians that the arc length is by the radius to get the angle in radians is if the angle is in radians. It has to be in radians. This formula is on your formula sheet. It's not something you have to memorize. It's not even something you have to understand in terms of radians and radii and all that. It's on your formula sheet, but it's a huge mistake that students will make that they forget that they have to be in radians. So if I give you an angle and ask you to use this formula to solve a problem, and the angle I give you is in degrees, well then you go back in time to yesterday and you use your skills to convert it to radians so you can use this formula. If I give you an arc length problem and you're asked to find the angle, but you're asked to find it in degrees, then you're going to use this formula to find the angle in radians and then use your skills to convert it to degrees. And along the way today, we only have a few examples to do, but along the way I'm going to show you that if all you care about is decimal values, not exact values, there's a way to convert from radians to degrees or degrees to radians on your calculator without writing anything down or setting up a ratio. But again, you understand that any written response, it's interesting because when I was marking the exam, somebody on their exam in the written response wrote not algebraically because I didn't use the word algebraically. Turns out they did it algebraically, but I don't have to write algebraically all the time. You should know that you could never do a written response by just saying, I did this on my calculator, right? Okay. So for a written response, what I'm going to show you today is no good. Let's take a look at an example. A 40 centimeter long pendulum swings through an arc of 35 centimeters. Determine the angle through which the pendulum swings in both degrees and radians as exact values and to the nearest tenth. So when you have a pendulum, what you're dealing with is some kind of mass that's attached to a string and it swings. So if it's just hanging straight down, I'm going to make this a little bit smaller. If it's just hanging straight down, nothing's happening. I think it's pretty obvious, but I will just explain it, that as a pendulum swings, since this point up top is a pivot point, the length of the pendulum acts as a radius of a circle, and it traces out through space a circular arc. This isn't a complete circle. It's not moving around and around in a circle, but it is tracing out a circular arc. And what you're told is that the pendulum is 40 centimeters long, and the arc it traces out is 35 centimeters. So, you don't have to draw this to scale, but 35 centimeters is a little bit less than 40 centimeters. If I were to kind of try to trace out an arc here, and you're going to have to do your best to draw things. I'm just cloning things so that I can get a half-decent diagram. I might say that from there, probably not, probably more like this. I mean, it doesn't have to be perfect. You need to understand the math. That this arc here is 35 centimeters. Right? Now, I actually, in retrospect, looking at it, I might have drawn one that's longer than 40. But you get my drift here? Okay. So the formula, and I'm gonna write it down this way because I can't help myself, and it's going to happen accidentally later. The formula is theta equals A over R, and when I was in high school, it was A equals R theta, and that has stuck ever since. If you take the formula theta equals A over R and multiply both sides by R, you get what I wrote. So I will, 9 times out of 10, probably write A equals R theta, because it pops out of my head. So what do we want to find here? Well, we take my formula, A equals R theta. We want to find theta, so let's divide both sides by R, and we get the formula on your formula sheet. All we have to do is take 35 centimeters divided by 40 centimeters, and we get an angle here. I'm not sure what you're doing here. We get an angle of 7/8 of a rad. That's my exact value. Now, we also want that angle in decimal form, and we would normally call this a decimal approximation, but when you take 7 divided by 8 on your calculator, you get 0.875, which is an exact value as well. We're going to say it's an approximate value if you get 0.8325, 6667, and it just goes on and on and on. So we could put 0.875 rads, or 7/8 of a rad. And now we want to convert this to degrees. So we go to yesterday's work. These are radians. I'm going to go degrees over here. You do not need to write the word rad. You don't. But why not? If it's a written response, why not write that to remove all doubt from the marker's mind that this student may or may not have a good understanding? Okay. So we set up this ratio, 180 degrees over pi radians equals x degrees over 7/8 of a radian. How do we get rid of that 8? We simply say to ourselves, I can multiply the top and the bottom of this fraction by 8. This is what we want to do when we see complex fractions. And if you can't handle this, and I'm not saying this to scare you, I'm saying it to motivate you, then when we get something like which we will, you will not know what to do with this. The answer is you would multiply the top and the bottom by cosine of theta. By the way, sine squared of theta means sine of theta quantity squared. Okay? So these are skills that I'm not just saying, oh, these are important because I'm a math teacher. They're important for you later on. When I do that, what I end up with is 180 degrees. I can cancel the degrees. I don't need to write degrees anymore. Over pi equals 8x over 7. And now it's a straight kind of cross multiplication thing. Multiply both sides by 7, multiply both sides by pi, which means you're cross multiplying. You get 7 times 180 equals 8 pi x. So I'm going to divide both sides by 8 pi. So I have 7 times 180 divided by 8 pi. And this is equal to x. This is going to be the angle in degrees. I believe I misspoke up here. Well, it's going to be degrees. I was going to talk about the units and the cancellation, but that's not important. We want an exact value, so you need to take 7 times 180 divided by 8 and reduce it down. And even though it's important you understand how to do that by saying I'm going to maybe multiply 180 and 8 both by 4, there's nothing wrong with going 7 times 180 divided by 8 on your calculator and going math, enter, enter. But leave the pi out of it, okay? Because the pi is irrational and we want an exact value. $315 over pi. 315 over 2 pi. This is a number of degrees, right? Going back to what I was talking about with the units, these are both degrees, right? So we're getting x degrees. You don't have to think of that with the unit there. You can just say, well, I'm finding degrees. Now let's find a decimal approximation here. So I would like everybody to enter in 315 divided by 2 pi on your calculator. Man, that's going to be very close to 50, isn't it? However, did anybody not get something close to 50? Like maybe 450? Yeah. And that's because you cannot enter 315 divided by 2 pi. You cannot enter it this way because your calculator, Eric, sees that and says, I'm asked to calculate that. There's a multiplication sign between the 2 and the pi that's unwritten. And that'll give you the answer that you got. So when you do this, you have two options. You can either put a set of brackets, which, how many of you did that? Or, I mean, the way I do it, this is just, again, going back to my high school, this is how I was taught to divide by product. So you just divide by each piece, and you get the right answer. Okay. Are we okay with that? So it's about 50 point, well, let's call it 50.1 degrees. I don't know what the question said in terms of decimals. I don't care. So we've got exact value with radians, decimal approximation with radians, which turns out to also be exact, and then exact and decimal with degrees. Now, I want to go back to this question where we had 0.875 radians. We can convert radians to degrees on your calculator without even, by just following a set of steps. The first thing to note is you need to be in the mode that you want to convert to. So by putting it in degree mode, the calculator recognizes every number as being degrees. And I'm about to show you something that's really stupid. If I say 60 and I hit enter, my calculator says it's 60 degrees. And I know that seems weird. Is this 0.875 degrees? That's radians. So what we have to do is tell the calculator that it's 0.875 radians and then hit enter and it'll tell us how many degrees it is. And we do that by slapping a radian label on that number. And there's a little sub-menu here, which is second apps, where it says angle. And if I choose that, my first three options are degrees. The second option is an angular measure called minutes, which you would use in navigation. And then radians. So if I do this, it looks like it's an exponent. It's not. It's just a label that's being attached to that number. I've entered the number 0.875 radians. So when I hit enter, since my calculator is in degrees, it's going to tell me how many degrees it is. Okay. And this is a very nice thing to use for numerical response questions where you can use decimals. Okay. Let's try another one. A circle of radius 8 centimeters contains a central angle of 132. Determine the length of the arc as an exact value and also round it to the nearest tenth. So it's A equals r theta. That means the arc length equals the radius, which is 8, times the angle in radians. We have to convert that 132 to radians. So we know that pi radians is 180 degrees. That means we can set that as being x radians over 132 degrees, which means x is 132 pi over 180. You know, quite frankly, I don't care if you simplify 132 over 180 right now, because you're going to take that angle in radians and put it here. So you can simplify all of these rational pieces to our answer in one fell swoop on your calculator. You know, you could tear it down and, you know, divide top and bottom by 4, divide top and bottom by whatever numbers, 5 maybe. 5 wouldn't work. But nobody cares about that at this level. We care about getting an answer here. So 8 times 132 divided by 180. And math, enter, enter. Because why not? 88 pi over 15. Do you get the same result? Okay, so it's 88 over 15, which means this is 88 pi over 15. And this is an arc length. This is a number of centimeters. It's not an angle. Just because you see a pi in there doesn't mean it's an angle. The pi is there because the angle had a pi in it, and then we multiplied by the radius. If you want to know a decimal value, then I guess we can just take this number times pi. So about 18.4 centimeters. Could we have converted the 132 degrees to radians on the calculator? Yes. And I'm going to show you two things here. One thing is obvious to everybody, you should understand this, is if all we wanted was this 18.4, we just wanted a decimal answer. We don't care about exact values. Then what you could do is you could take your calculator and put it in radian mode, because we're going to convert to radians. We have to take that 132 degrees and write it as radians. So I go 132. I go to my angle submenu and I slap a degree label on it. This is the number of radians in decimal form. And now if I multiply that by, what was it, 8, I get the answer. Okay. Just for kicks, and this is the part that not everybody's going to get, can you simplify this angle for me? Like, what is 132 over 180? (11 over 15). This is 11 pi over 15. Whenever I have to write 11 beside pi, I always separate it because it just looks wrong to me. Could we have found this on our calculator? Yes. We could have done this. We could have entered this, right? Hit enter in radian mode, and that's the radians. Now, if I try this little trick, math, enter, enter, it goes nowhere because that's an irrational number. Why is it irrational? Because it's a multiple of pi. So if I want an exact value here, and I know this is a multiple of pi, why don't I divide pi out of it and convert that to a fraction? Now that's not, on a written response, and this is something that people will often not realize, converting radians to degrees, even as exact values, is really simple. But you need to show your work on a written response. Okay. All right, let's try one more. Oh, another clock. The minute hand of a clock is 30 centimeters long. As an exact value, and also to the nearest tenth, what is the distance traced out by the minute hand during a 75-minute class? Well, 75 minutes, we have to sort this out. And because it is a clock, let's start here, because the minute hand moves this way. You should understand that 75 minutes takes you all the way around to here and then ends here. 75 is 15 more than 60 minutes. We're not talking angles here, we're just talking minutes. So this is the angle that we're talking about. Well, since we're going to have to use the formula A equals R theta, and R is 30, and theta is in radians, why don't we just count out how many radians that is? So if you watch well, I'll do it here just in case you're watching this video later. Starting here, so this is a very non-standard thing. I'm starting there at 0. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, it's 5 pi over 2. There's no need to figure out that it's, 450 degrees, and then convert that to radians. We can just count off pi over 2's, which are 90 degrees. So 1, 2, 3, 4, 5 pi over 2. And for all intents and purposes, we're done. 30 divided by 2 is 15. 15 times 5, I think, is 75. So can somebody confirm that this simplifies to 75 pi? Good. Thank you, Claire. And if you want a decimal approximation, just take 75 times pi. So it's about 235.6 centimeters. Are we okay with that? Okay. One last example. I don't care for this diagram, but I pulled it from a resource from Alberta Learning, and they used it on a diploma exam. So what you have is a wiper blade on the back of an SUV. The SUV has been caked with mud or dirt, and the wiper blade has gone through and cleared a clear spot. And you're asked to determine the perimeter of the cleared space. The thing that I don't like about this diagram, and I kind of get why they did it, is this little kind of shape here that the 150 degrees has a line connecting to. It really ought to be the same color as this other dark spot. It's caked with mud as well. And for some of you, I know you go, wow, what's the difference? Honestly, the first time I saw this question and it said find the perimeter, my first thought was to find this. Because I didn't realize that little kind of weird shape in there was not part of the shape that I'm trying to find the perimeter of. In reality, and then I realized quite readily that that's what I had to do. In reality, you need to determine that arc length, this arc length, and add those two arc lengths to 16 inches and 16 inches. Okay? So what we're going to do is calculate two arc lengths. We're going to calculate little a, which is little r times theta, and we're going to calculate big A, which is big R times theta. I'm just using capital to signify the larger arc. When we take a look at the radius here for the little arc, it's 4 inches. And boy, I'll explain this. I don't want to just throw it out there and move on. But you should know by now, hopefully, that 150 degrees is 5 pi over 6. Like you should almost, if you look at my arm here, here's 0, You should almost, when you see this 5 pi over 6, you see 150. 1, 2, 3, 4, 5 pi over 6. And as the days go on, it will become more and more obvious. This is 20 pi over 6. I'm not going to simplify that. You'll see why in a second. It's 20 pi over 6. When I do the same thing over here, 5 times 4 is 20. What do I get? Well, I get the radius. Now, what's the radius of the big arc? It's 20. The arc doesn't have a radius. What's the radius of the circle that that arc is on? Well, this is the radius. Right? The pivot point is where that arm of the wiper is attached. It's not pivoting from that 4-inch mark. So that's a 20-inch radius times theta, which is still 5 pi over 6. And the reason why I'm just going to leave these as pi's over 6, I guess we could reduce them down. I guess we could reduce them down. Is they have a common denominator. Are you with me on that? Does it matter, I guess? I don't know what I was thinking. This is 10 pi over 3. This is 50 pi over 3. Doesn't matter. I'm going to put them together. Let's get our perimeter here. Our perimeter is 20 pi over 6 plus the 100 pi over 6 plus the 16 for the left-hand piece and the 16 for the right-hand piece, and we can put them together. This is 120 pi over 6. This is 32. 120 pi over 6 is 20 pi plus 32. 120 divided by 6 is 20, last time I checked. We okay there? We don't want to fumble around on the calculator here because this is a numerical response and we want an exact value with this A, B, C, and D. How was this question structured? The answer was A pi plus B. So when we compare our answer with the template they give us, A is 20 and B is 32. So the 4-digit answer, we would have a 4-digit answer here of 2032. The first time these questions came out were, for years and years, if they said A was a single digit, always, always, always. And then about 4 or 5 years ago, they started peppering in stuff like this. A little ticked off by it, but you get used to it, okay? It's not a big deal. Be careful here, and I didn't do this by design, but when I wrote this down, I happened to write these first. Had I written it the other way around, I would have ended up with, you should be able to be adaptable here, 32 plus 20 pi. I hope you understand that 32 is not A. 32 is B, and 20 is pi, right? Or 20 is A. All right, that's it. That's all. Number of questions on those pages seem right to you? They are not right, are they? This would probably be 7, 8, 9, and 10. 9 and 10.